Welcome to Daily Space, your daily dose of cosmic wonders and astronomical discoveries. In today's episode, we're delving into why time slows down as we speed up. Before we launch into the cosmic adventure, make sure to give this video a thumbs up if you're excited to learn about today's topic. Don't forget to comment your thoughts and questions down below, and if you're new here, be sure to subscribe and ring the notification bell so that you never miss another journey through space. Now, let's dive into why time slows down as we speed up. Imagine setting out on an exciting space mission. Packed with anticipation, you're ready to go on an extraordinary adventure. As you step into the spacecraft, you're informed that your journey will involve traveling at nearly the speed of light, and you'll return in just 2 years. Without much thought, you gear up for launch more excited than ever before. Upon your return, an astonishing reveal awaits. Everyone you know has aged by 14 years. How could this be? The phenomenon behind this mind-bending experience is known as time dilation, a concept discovered by none other than Albert Einstein through his revolutionary theory of special relativity. But what exactly is time dilation? First, let's grasp a fundamental truth. Time isn't uniform, it is relative and behaves differently in various situations. This is something we don't notice in our day-to-day life as the change in time is so small. To give you an example of how small this change is, let's imagine you and a friend want to see the difference in time for yourself. So you decide to do an experiment in which one of you will stay on the ground with a stopwatch and the other will fly in a plane for 8 hours at approximately 900 kilometers per hour, also having a stopwatch which both of you start at the same time. When you land and compare your stopwatches, you notice that the stopwatches have a time difference of 0.00504 seconds. In 1971, a study known as the Haffel and Keating experiment was conducted by the United States Naval Observatory using atomic clocks and airplanes. Atomic clocks can measure beyond hours, minutes, seconds. 2 planes were to fly in opposite directions around the globe, one towards the east and the other west, both carrying their own atomic clocks, whilst there was an additional reference atomic clock stationed on the ground. From their individual flight paths and speeds, Einstein's theory of time dilation predicted that the atomic clock on board the plane flying east should have lost time while the one flying west would have gained time. The results were astonishing. The atomic clock flying east lost 59 nanoseconds and the one flying west gained 273 nanoseconds. We can also look at time dilation by looking at this formula which Einstein discovered. We can use the mission we talked about in the beginning as an example. The left T describes time measured by a stationary observer. The T to the right describes tone measured by the moving object, in our case the spacecraft. Then V is the speed of which the aircraft is moving, which is 0.99% of the speed of light, and C is the speed of light. Now all we have to do is to plug in our numbers. So our time measured is 2 years. The speed we are moving with is 0.99% the speed of light. Now the C's cancel out, so we are left with 0.99, which we make to the power of 2. And lastly, we divide 2 years by this number, and we see that for the stationary observer it has passed 14 years. We will also talk about the advantages of this time dilation and how we can make use of it in an upcoming video. The phenomenon of time dilation can be understood through the concept of spacetime. Special relativity puts forward that spacetime is a 4-dimensional continuum, where 3 dimensions represent space and the 4th dimension represents time. When an object accelerates to high speeds, it navigates through spacetime in a way that changes the relationship between time and space. From the perspective of an observer in motion, time dilation occurs because the intervals between events in spacetime appear stretched compared to an observer at rest. This effect becomes more pronounced as the object's velocity approaches the speed of light. As velocity increases, time itself dilates, causing time intervals to become longer as observed by an external stationary observer. Time dilation is a direct consequence of the speed of light's constancy and the intricate interplay of spacetime dimensions. The faster an object moves through space, the more its internal clock appears to slow down, shaping the unfolding of events in the universe. Thank you for joining us on this cosmic journey today as we delved into why time slows down as we speed up. If your curiosity was sparked, don't forget to show your support by giving this video a thumbs up. If you're new here and hungry for more space exploration, consider subscribing to our channel and becoming a part of our passionate community. We'd love to hear your thoughts, questions, or even ideas in the comments below for our next adventure together. Our cosmic voyage doesn't end here. Stay tuned for more captivating explorations into the universe's secrets. Until then, keep looking up, keep dreaming, and keep exploring. And thank you for watching Daily Space.